Good morning, everyone. I wanted to go ahead and then um, this video will be the point where we really introduce the final topic of the year. So what I have set up right here is a bit of a lab. I'm not going to make you do it, although I will save this and give it to you if you want to use it. But what this is just a quick little setup where I have a single battery pack pushing current through a whole bunch of different long bulbs, and then a battery pack set to the same value, pushing current just through a round bulb. And what I've been doing is I've been changing the amount of voltage. Remember, that's the pressure difference. I've been changing the pressure difference across each bulb, across each battery pack. So like this would be like I just removed 5 batteries from it. And what we can see is we can see how the light bulbs are responding. We can see how the current flow is responding. We can see it all propagate through. And then what I'm doing is I'm looking at how the current responds. So I did that just a second ago for like 4 or 5 different cells. I originally was going to show you the whole thing, and then it took forever, and then I messed it up. So yeah, we're just skipping ahead. So I already have taken the data, and it's right here. So I want to take a moment and I want to look at this. We have 4 lines here, and our 4 lines. I'm going to apply a curve fit to them. Here are our 4 lines. So this is measuring if we put through this much current, how much of a voltage drop will we need? So here, notice here, we get a large amount of current with a relatively small amount of voltage. So you can imagine in our 4 different circuits that we had, our 4 different paths through there, this blue one was the easiest one to get current through. Because look, I only need a 1.5 volt voltage drop to get like a 0.8 current flow. To get a 0.8 current flow here, in this one, I needed a 3.5 voltage drop. To get a 0.8 in this one, I'm going to need like a 9. I haven't gotten that far. So this graph right here is showing us basically what amounts to resistance. So here's what I'm going to do is I'm going to copy over this data and paste it into my drawing software real fast. So looking here we have our 4 lines, and I'm going to go ahead and mark which one is which. So first off, this one right here is the line for just our 1 round bulb. You'll see it has the smallest slope, which means that for any given current, it doesn't require much voltage. This next one is our 2 long bulbs. Let's feel the color. 2 long bulbs in parallel. It's a little bit steeper. The purple here, this is our 1 long bulb. And then finally, the pink here is the 2 long bulbs in series. And I bet you some of you already can tell what's going on here. Why would this 2 long bulbs in series have by far the steepest line? And let's think about what that means. In order to get, let's say, a 10th, let's not do a 10th of an amp. In order to get a 20th of an amp, right, that's 0.05 amps, we would need something like 9 volts to get it through 2 long bulbs in series. If I wanted to get that same amperage, though, for 1 long bulb, I don't need as much voltage. If there's only 1 long bulb, I only need like 4 volts. If there's 2 long bulbs in parallel, I only need like 1.5 volts. And finally, for a round bulb, I hardly needed anything. I needed like less than half a volt. Like 1 cell doesn't even need it. So what we see here is to get this 1 current, each of these different circuits require a different pressure drop. We see this by looking at the slopes. So what I'm going to do is I'm just going to copy down the slopes onto this chart. So our round bulb has a slope of about 29.6. And this is volts per amp. So for every amp I want to push through, I need this many volts. This blue one here, 45.9 volts per amp. For every amp I want to push through my circuit, I need 45.9 volts. Next one, 91.8. For every amp I want to push through my circuit, I need 91.8 volts. And then finally, 228.3. That is the number of volts I will need to push every amp. So this slope right here tells us how hard it is to push an amp of current through a circuit. If I want to push 1 amp, here's how many volts I need. You know what this sounds like to me? This is the resistance. That resistance that we've been talking about all year is represented by the slope of this line. This 29.6 volts per amp is a description of how difficult it is to put current through our circuit. So in a way, the equation for this line would look like this. Y equals mx plus b, right? The voltage is equal to the resistance, this 29.6 volts per amp, times the current, which is capital I. So we now have this nice little pretty straight line equation that describes, hey, if I have this much current and this much resistance, here's how much of a voltage I'm going to need. Here is how much of a voltage drop I am going to get. Now, a few little changes. This is always true. So I could make this equation for any of these lines. This volts per amp thing gets really awkward because like this V is the symbol for voltage and I got a V here and it just confuses people. And so they did something kind of silly. You can love it or hate it if you want. They replaced this with a new symbol. They used this symbol called an ohm. I don't know if you recognize that. That is a Greek letter omega, but all it means is the number of volts required to push 1 amp. So you'll commonly see that written, 29.6 ohms. This is the resistance. So succinctly, you'll commonly see this written like this. The voltage running through any single circuit will be equal to the resistance of that circuit times the amount of current flow going through that circuit. This equation right here is sort of relating all these three things that we've been talking about all year together into one spot. And the reason why we spent so much time thinking about lines and relationships in lines is I wanted you to see where this equation comes from. It's the relationship between the amount of current we want to put through a circuit and how hard we're going to have to push to make that happen. Target 4 is all about using this equation and making these predictions. So let's just give you a quick example. Let's go ahead and take our round bulb, 29.6 ohms. If we have a round bulb, and we're going to go ahead, and yes, it's 29.6 ohms. And if we are going to attach it to a cell that has a, let's go ahead and make it, a 9-volt cell. So one of our 9-volt batteries. If we were to attach a 9-volt battery to a single round bulb, what would the current flow be? This would be the sort of question that I could ask you here. So how would we solve for that? What I'm going to do is I'm going to start just plugging these numbers into our equation. The number of volts, 9 volts, will be equal to my resistance, 29.6 ohms, times I, the current. I don't want to use ohms right now because like I have volts over here and I want to be able to cancel units out. So I'm going to rewrite this now as volts for every amp. And what we end up seeing is that volts can get canceled out from both sides. Finally, I want to get I by itself. So what I need to do is divide both sides by 29.6. So down here, I is equal, so excuse me, the 9 volts, we've got cancel out the volts, divided by 29.6 per amp will be equal to my current. So when I check on my calendar, my calculator, I end up getting a current of 0.30. When I solve for this, I would predict a current of 0.30 amps. And we're done. That's our prediction. So I'm hoping here that you can see A, how we got these lines, what these lines represent. B, that when you look at these, we can see, oh, look how easy it is to push current through this one. Look at how hard it is to push current through this one. And then to see that that slope seems to tell that story. The slope tells the story of how difficult it is to push current through one of these 4 loops. Finally, we can look at the equation that we get from this, and we can get this relationship right here, that the voltage running through a circuit will be equal to the circuit's resistance times its current. And it doesn't have to be for the whole circuit. It can be for any individual component. This relationship helps us really put together these 3 things from earlier in the year. So, please let me know if you have any questions. This is a relationship I do expect you to know. This is something I expect you to use, and this is the last target of the year, and I'm going to be honest, it's just multiplying numbers, or maybe a little bit of division, tiny bit of algebra 1, right? I think you guys can handle that. All right, everyone, let me know if you have any questions. Have a nice day.